Well, hello, this is Mr. Doro. Today we're going to be talking about gas laws. By the end of this video, I'd like you to be able to use gas law equations to determine how variables will change in those equations. Well, the gas laws are simple mathematical relationships that happen between those variables for gases that we've talked about before: volume, pressure, temperature, and the amount of gas or the moles of gas. These are people who have come up with some of the gas laws. This is Robert Boyle. He came up with Boyle's law. This is Jacques Charles, who came up with Charles' law. This is Joseph Gay-Lussac, which is Gay-Lussac's law. This is Amedeo Avogadro for Avogadro's law. Well, the first thing we're going to do is we're going to take a look at Boyle's law, and I really want you to pay attention to the relationships between the two things that Boyle studied, which were pressure and volume. Now, it's important to know that he had to keep constant the other two variables, the number of moles, so he didn't change the amount of gas, and the temperature. He kept those the same. So if you look at this graph, up here on the top, we had a pressure of 1 atmosphere. That's the pressure of the gas that's contained inside of here. And the volume was 4 liters. If you multiply the pressure times the volume, you get 4. 1 times 4 is 4 atmosphere liters. Now, if you decrease the volume by half, and then what's going to happen to the pressure is the same number of molecules that are in here, they're going to hit each other more often, and they're going to increase the pressure. So volume decreases, pressure increases. But if you multiply them, 2 times 2, you still get 4. And then even further down here, you decrease the volume even more, down to 1 liter, the pressure increases. Now that pressure should say atmospheres up here. And the pressure is 4 atmospheres, and you multiply the two of them, and you still get 4. Now, here's what Boyle found out. Boyle found out that pressure and volume are inversely related to each other, which would be written like this: pressure times volume equals a constant. That K stands for constant. So as pressure goes up, increases, then volume must go down. And they have to go down by the same factor, or inversely related. Therefore, if we figure out the initial pressure and volume, in a new pressure or volume, we can figure out the other variable. So we got Boyle's law, and this is what Boyle's law ends up being right here. P1, V1, and the ones are initial, and equals P2 times V2, because they're always going to equal a constant number. And so if you look at this, decreasing the volume increases the collision and increases the pressure, and we had a volume of 1 liter here and the pressure of 100 millimeters of mercury. When we decrease the volume, or decreased it by 1/2, then it doubled the pressure. And that's what Boyle's law states, that relationship. Now, Boyle's law can only work if the volume can change. That means it's not a rigid container. So if you look at this, we have the skinnier guy here standing on this, and then we get one that's a little bit heavier, and that increases the pressure on here, which decreases the volume, and then we get the larger gentleman here, and that increases the pressure even more, which decreases the volume. Now, if that container were a rigid container that they were standing on and it didn't change, it wouldn't change the pressure or the volume either way. Now, the next law is Charles' law, and Charles' law deals with volume and temperature right here. And so you can see what happens. Again, this is not a rigid container, because otherwise the volume wouldn't be able to change. And so the initial volume, you can see that we have the gas is taking up that area. We increase the temperature right here, and as we increase temperature, you can see it's increasing here, then the volume increases also. That's because we are keeping pressure and the number of moles constant. And so these are directly related to each other. And here's how you would write a direct relationship. V over T, volume over temperature, is a constant. Once again, though, it's important that you know that the pressure does not change and the number of moles, or the amount of gas, does not change in Charles' law. Here's another example of Charles' law with this cylinder, and you can see that at a very low temperature right here that the volume is very small, but as we increase the temperature, in order to keep the pressure the same, because pressure is constant, then the volume has to increase also. And so what we end up with is that volume over temperature, and then Charles' law, then we can find a formula of initial and final, just like we did on the other one. V1 over T1 equals V2 over T2. Now, the important part of this is that these temperatures right here must be in Kelvin. And Kelvin, remember, is Celsius plus 273. So This Kelvin right here is degrees Celsius plus 273. So if you're given a temperature in degrees Celsius for gas laws, always change it to Kelvin by adding 273. Now make sure that you have this formula right here written as Charles' law. That's what it is. V1 over T1 equals V2 over T2. Then we have Gay-Lussac's law. Gay-Lussac's law deals with pressure and temperature. And so we have to keep some things constant in this one also. We have to keep the volume the same. So it's a rigid container. It cannot shrink or it cannot expand. And the number of moles, we don't add any gas or subtract any gas from it. And so you can see what's happening right as we look up here. That we have a pressure reading, we have a temperature, and we have these moving. Those smaller arrows mean that they're not moving quite as fast with each other. When we double the temperature, which is what this is doing right here, then you can see that it is also doubling the pressure because they're hitting each other more often. And so that would be a direct relationship. As one goes up, the other goes up by the same account. This is a direct relationship right here. P1 or P over T equals a constant, and that temperature must be in Kelvin. Here is what Gay-Lussac's law would look like. P1 over T1 equals P2 over T2. Make sure you have that written down for Gay-Lussac's law. So here's just a brief overview of what we just went over. When you have all of these have the number of moles of gas constant, so we're not adding or subtracting gas from it. But when we have the temperature constant, we have P1 V1 equals P2 V2. That's Boyle's law. Volume constant, P1 over T1 equals P2 over T2. That's Gay-Lussac. And pressure constant, V1 over T1 equals V2 over T2. That's Charles. Well, we can put all three of those together to make something called the combined gas law. You're going to want to write down the combined gas law. It is this P1 V1 over T1 equals P2 V2 over T2. It does keep the number of moles constant, but this is where all of these other ones can change. And really all the other laws can be derived right onto this too. So if I were to cross out, if I were to say pressure was constant, then we would get rid of pressure on this side and pressure on that side because they would cancel each other out if they're the same number, and we would end up with V1 over T1 equals V2 over T2. Same thing if temperature was constant, I'd cross this one out and that because they would cancel each other out. They're the same number, and I would end up with Boyle's law. P1 V1 equals P2 V2. And so the combined gas law is very handy to know how to use. Well, here's a sample gas law problem that you might see, and you might not know what type of law you're going to use on it until we start to read it. But what I like to do is I like to use the units to tell me what each of these variables are measuring. For example, the first one says a 1.50 liter balloon. Now, liters is a unit for volume, so I'm going to put a V right above it. Has an initial pressure of 2.10 atmospheres. Atmospheres is a unit for pressure. At what pressure would the balloon have a volume of 2.50 liters? That's another volume, assuming constant temperature. Ooh, that's important too. Constant temperature. And so really what I have to do is I have to put these together. This volume and this pressure go together because it says it's 1.5 liters at this pressure. And so I'm putting those as the initials, the ones, V1 and P1. And then my new volume is 2.50 liters, so that's my V2. So I pretty much know I'm not going to need temperature on this, so I'm going to set up my formula like this. P1 V1 equals P2 V2. Now notice, I really like when you label these, otherwise you have to, if you don't label them up here like I did, then you're going to have to list down here, P1 equals so on and so forth. That's a lot more work, so just do it this way. Then you just plug them in. The P1 is 2.10 atmospheres. The V1 is 1.50 liters equals P2, which is, we don't know, we're going to solve for that, the new pressure, and 2.50 liters right here. These are both liters, so that they're going to cancel out. In order to get the P all by itself, then I have to divide both sides by 2.50 liters, and so that's over 2.50 liters, and I end up with 1.26 atmospheres. Now, I did that in the correct number of sig figs also. They all had 3 sig figs. And also, I just want to take a look and make sure that this makes sense, because the pressure went from 2.10 atmospheres to 2.5, so the pressure went up. These are inverse relationships, so the volume should have went down. And at 1.5 down to 1.26, oh good, that does make sense. So I probably did it right, and that's my answer. Okay, so here's another example, and so I'm just going to start going through here, and I have first of all 55.0 centimeters cubed. I know that's a volume. It says at STP. Now that means something. That means standard temperature and pressure, and that's where I'm saying look to the stars from the last video that we had. Standard temperature is T equals 273 Kelvin. And then standard pressure is that we have a bunch of different pressures, but I want to match it up with my other pressure that I'm given, which is kilopascals. So that's 101.325 kPa. And so those all go together. This is going to be my V1, this is my T1, and that's my P1. And then I'm also given is heated to, so I'm heating it up, I'm changing my temperature to 95 degrees Celsius, which is going to be my T2. But that's in degrees Celsius, so I need to change that to Kelvin because I always need Kelvin. So now I've done that. 95 plus 273 gives me 368 K. That is my T2. And then I also have a new pressure right here. That is my P2. The pressure was increased to that. It wants to know what the new volume is. Hey, I've got 5 different things here, and I've got to solve for one more. This has got to be the combined gas law. P1 V1 over T1 equals P2 V2 over T2. Again, write that formula each time. Then just plug in what you know, which I'm going to do right now. Okay, now I plugged it all in, and I get this big old mess right here. And so that may scare some of you about how to solve for V2, which is what I'm looking for. But I just got to get V2 by itself. It's already in the numerator. So I multiply both sides by 368. So really bring that 368 over here. Divide both sides by 110.6 kPas. Look what's going to happen to these units. The kPas are going to cancel each other out when I bring that kPa down there. The kelvins are going to cancel each other out. Here's what I'm left over with, centimeters cubed. So I'm going to plug this in right now. And in 3 sig figs, I got 67.9 centimeters cubed. If you have no idea how to do that, this is what I did. 101.325 times 55 times 368 divided by 273 divided by 110.6. So you should be doing these, by the way, in your notes. You should be practicing these. These are ones that I'm showing you so that you can understand how to do them. So now I've got a series of 5 questions that I want you to do at the end of your notes. First of all, I want you to look at this chart. This is volume versus temperature, and it's showing at 2 different points what these end up looking like. It's this situation and this situation, and I want to know whose law would that represent? Boyle's, Charles, Gay-Lussac, or the combined gas law. So you go ahead and do that one. And then for number 2, I want to know whose law does this one represent? This is pressure versus temperature. And again, showing you what's happening at the different stages. And so pressure and temperature on this one, whose law does that represent? And for number 3, we have the pressure versus volume. And you can see what's happening. This is high pressure, low volume up here. Volume's increasing, pressure is decreasing. Whose law does that represent? And for number 4, I have a balloon that has a kind of like a straw stuck in between it. One of the balloons, balloon B, is underwater. Balloon A is in the air. If they both start with the same amount of air, which one will end up bigger and why? That takes quite a bit of thinking, so think through that one. Pause it on that. And one calculation problem for you. It is a cylinder with a movable piston, contains 3.96 liters of a gas at 25 degrees Celsius. What would the new volume of the gas be when the temp is increased to 90 degrees Celsius at constant pressure? Word of warning for you, those temperatures were given to you in degrees Celsius. Remember, when we're dealing with gas laws, we always want to change those over to Kelvin. Have a great time working these out. Bye-bye.